Imagine a world where the tiniest building blocks of the universe are not point-like particles, but vibrating strings. This is the essence of superstring theory, a mind-bending idea that aims to rewrite our understanding of the cosmos. Like the strings of a cello producing different notes, these tiny strings vibrate in various ways, giving rise to all the fundamental particles and forces we observe. This revolutionary concept promises to unlock some of the universe's deepest secrets, including the nature of space and time, the origin of the universe, and the unification of all fundamental forces. Superstring theory is a journey into the heart of reality, where the universe's most profound mysteries might just be an elegant symphony of vibrating strings. For centuries, physicists believed that atoms were the smallest indivisible units of matter. Then came the discovery of even tinier particles like quarks and electrons. String theory takes this quest for the fundamental building blocks a step further, proposing that these particles are not point-like dots, but rather tiny one-dimensional strings. These strings are incredibly small, far smaller than anything we can currently observe. Imagine shrinking an atom to the size of our solar system. In this scenario, a string would be about as big as a tree on Earth. Despite their size, the way these strings vibrate determines the properties of the particles they create, just as a violin string produces different notes depending on its vibration. Different vibrations of these fundamental strings manifest as different particles with unique masses and charges. One of the most intriguing aspects of superstring theory is its requirement for extra spatial dimensions beyond the familiar three we experience. While this might seem like something out of science fiction, these extra dimensions are curled up or compactified into tiny spaces, too small to be detected directly. Imagine a tightrope walker moving along a cable. From a distance, he appears to move only in one dimension, along the length of the cable. However, an ant crawling on the cable experiences an additional dimension, the circumference of the cable. Similarly, our universe might have these hidden dimensions curled up at every point in space, invisible to our current instruments. Section 4. The Quest for Unity, Superstring Theory, and the Forces of Nature. In the universe, we observe four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Physicists have long sought a single unified theory that could explain all these forces as different aspects of one underlying principle. This is the goal of the theory of everything. Superstring theory offers a promising framework for achieving this unification. It suggests that all forces and particles emerge from the different vibrational patterns of these fundamental strings. Just as a single musical instrument can produce a variety of sounds, superstring theory proposes that the universe's symphony of forces and particles originates from the harmonious vibrations of these tiny fundamental strings. Section 5. A tapestry of theories from strings to membranes. Initially, there were 5 different versions of superstring theory, each with its own mathematical framework and set of predictions. However, further research revealed that these seemingly distinct theories were connected and could be unified under a broader framework known as M-theory. M-theory proposes that the fundamental building blocks of the universe are not just one-dimensional strings, but also higher-dimensional objects called branes, short for membranes. These branes can have various dimensions, and their interactions could give rise to the different string theories we observe. M-theory is still under development, and its full implications are yet to be understood. Section 6. Unraveling the mysteries, challenges, and future horizons. Despite its elegance and promise, superstring theory faces significant challenges. One major hurdle is the lack of experimental evidence to support its predictions. The extremely small scale of strings makes it incredibly difficult to design experiments that could directly observe them. Another challenge lies in the complex mathematics involved in the theory. Even with advanced mathematical tools, understanding the full implications of superstring theory and making testable predictions remains a daunting task. Nevertheless, physicists are developing new theoretical frameworks and experimental techniques that could potentially provide evidence for superstring theory in the future. These include searching for subtle effects in cosmological observations, exploring the behavior of black holes, and probing the nature of dark matter and dark energy. Superstring theory, while still in its infancy, offers a tantalizing glimpse into the universe's deepest secrets. Its potential to unify the fundamental forces, and explain the fabric of reality makes it one of the most exciting and challenging areas of modern physics. As we continue to unravel its mysteries, we might just discover the universe's ultimate secret code, written in the elegant language of vibrating strings.